All right, good morning, everybody. So I'm going to go over the midterm problems and answers. Any questions before I start? I think the grades were all posted yesterday. Good. So let me just get everything going properly. All right, so problem one. Remember, if you have groups G1 and G2, a function f from G1 to G2 is a homomorphism if f of xy is f of xy for all xy in G1. And in this problem, we have the group G1 and the group G2 both equal to R times. This is the R, all the real numbers without zero. That is this is the multiplicative group of non-zero, positive and negative, but non-zero real numbers. The group operation is just ordinary multiplication. And f of x is x squared. And part A is to prove f is a homomorphism. So that means we have to prove that this relation is satisfied for all non-zero real numbers x and y. So what is f of xy? It's xy squared. What does it mean when you square a number? You multiply it by itself. By associativity, this is the same as x times y, x times y. I didn't rearrange the order, I just bracketed the terms differently. But our group is a billion. R star is a billion. That means xy equals yx for all x and y in the group. So I can write yx as xy, which is x times x, y times y. That's exactly x squared, y squared. And x squared is f of x, and y squared is f of y. So this relation is satisfied. F of xy is f of x times f of y. Therefore, f is a homomorphism, a group homomorphism. Okay. Any questions about this? What is the image? So whenever you have a function from one set to another, whether they're groups or not, the image of f is the set of all elements, say y over in G2, such that y equals f of x for some x in G1. I mean, the picture you should always have is here's G1, here's G2, there's some map f between them. And so if you take any element x in G1, it gets sent to f of x or y in G2. But it's not necessarily the case that every element in G2 is the image of something in G1. You will normally have some subset of G2, which is the images of all the elements in G1. And this green space is the image of F. So we have to find the image of F for our function defined by f of x equals x squared. And what can we say? Well, first of all, x squared is positive for all x in R star. That is, if you take a non-zero number and square it, you get a positive number. And every positive number has a square root. So the image of F is the set of all x in R star that are strictly positive. So the positive real numbers form a subgroup of the multiplicative group of all non-zero real numbers. But that's the image. What is the identity element? So that's part B. In part C, we want to find the kernel. Now, what is the identity element in R star? It's just the number 1, right? 1. 1 times x and x times 1 equals x for all x. And the kernel of F is the set of all x in R star such that f of x equals 1. It's all the elements that get mapped to the identity. That's all x in R star. What is f of x? It's x squared. X squared equals 1. What numbers, when you square them, give you 1? Well, they're just two of them, 1 and minus 1. So the kernel of this homomorphism is just the two numbers, plus 1 and minus 1. That's k. And if we take the left coset 7k, that just means take everything in the kernel and multiply it by 7, so you get plus 7 and minus 7. And that is what it is. That's it. Any questions about that? So this function f of x equals x squared has to be one of the world's basic, simplest homomorphisms, and it gives a nice example of just knowing the meanings of the words: homomorphism, image, kernel, coset. Okay. Problem 2. So gamma 18 is the cyclic group of order 18 generated by X. I just have to pause for 1 second. So gamma 18 is the cyclic group generated by X. So it means we have all powers of X, and they keep going, but in the cyclic group of order 18, x to the 18th power is the identity. So you have exactly 18 different elements in this group. The identity, which is like x to the 0 up to x to the 18th. So what's the order of x cubed? So the order of x cubed is the smallest positive integer k, such that x cubed to the k is the identity. X cubed to the k is x to the 3k. So what are these multiples of k? 3, 6, 9, 12, 15, 18. When you get it, this is make a little table. K and 3K. So 1, 2, 3, 4, 5, 6. When K is 6, 3K is 18, you get the identity. So the order, the smallest K, for which x to the 3K is the identity, is 6. The order of an element is the smallest positive power of the element. And positive means strictly greater than 0. The smallest positive integer k, where the element to the kth power is the identity. We're looking at the order of x cubed. So x cubed to the kth power is x to the 3k. If you look at the multiples of 3, the first time you get it to an integer divisible by 18 is when k is 6. X cubed to the 6th power is the identity. So the order of x cubed is 6. And in part B, define the subgroup H of gamma to the 18 generated by x cubed. You just take the powers of x cubed. You have e, x cubed squared, which is x to the 6th. These are just the multiples of x cubed. X to the 12th, x to the 15th, and x to the 18th is the identity. We have exactly 1, 2, 3, 4, 5, 6. These are the 6 elements in the subgroup H. So this is the subgroup of gamma 18 generated by x cubed. And what is the quotient group? So a quotient group is all left cosets AH, for A in the group. And you have, for example, E times H, which is the same as H. X times H, what would XH be? XH, you multiply every element in the group by X. You would get X, X to the 4th, X to the 7th, X to the 10th, X to the 13th, X to the 16th. The next would be X to the 19th, but X to the 19th is the same as X. What about X squared H? If you multiply every element in H by X squared, you get X squared, X to the 5th, X to the 8th, X to the 11th, X to the 14th, X to the 17th, and X to the 20th will be the same as X squared. And if you look, these 6 elements, these 6 elements, and these 6 elements, that's the whole group. You have exactly these 3 cosets. So gamma 18 mod H, the quotient group, is this. And you can see just from looking at this that the index one, 2, 3. There are 3 cosets. You could also get this directly from Lagrange's theorem. It's the order of the cyclic group divided by the order of H. The cyclic group has 18 elements. The subgroup H has 6, and 18 over 6 is 3. But in any case, the index, the number of left cosets, is 3. Okay, any questions about this? So these are all calculations, but to do the calculation, you have to understand the definitions of the terms that we use in group theory. Let's look at problem 3. So we have a group G1 with identity E1 and a group G2 with identity E2. And we look at the product of these two sets, or the product of these two groups. This is a set of all ordered pairs, x1, x2, where x1 is in G1 and x2 is in G2. So this is exactly what you are familiar with, let's say in pre-calculus, where you're looking at the xy plane. And the point in the plane is coordinates xy. This is R1 plus R1. This is what you learn in, I guess, in high school, wherever you learn about points in the plane. And so this is the plane, R2. But if a point in the plane is an ordered pair xy, where x and y are real numbers. And the real numbers form additive groups, and you have this additive group of vectors in the plane. And this is just sort of the slightly more general framework into which this fits. You look at all ordered pairs, G1 and G2, where x1, x2, where x1 is in the group G1, x2 is in the group G2. And we usually write groups multiplicatively, and we define the multiplication in G1, G2 as follows. If you have x1, x2, and y1, y2, the way you multiply them is you just multiply coordinates, x1, y1, x2, y2. So this is the multiplication. And we want to show that this turns the product of two groups into a new group. So what does it mean to have a group? You have a multiplication that's associative, there's an identity, and every element has an inverse. So that's what we're going to check. Those are the three parts of the problem. So we want to show that multiplication is associative. So let me do it just very carefully. You take x1, x2 times y1, y2, and you multiply them. And then you take the product and multiply it by a third element, z1, z2. So in these square brackets, what you have is when you multiply these two elements, x1, y1, x2, y2 times z1, z2. And again, multiplication is coordinate-wise. This is x1, y1 times z1, x2, y2 times z2, disordered pair. But G1 is a group. So in G1, x1, y1 times z1 is the same as x1 times y1, z1. And G2 is a group. x2, y2 times z2 is the same as x2 times y2, z2. So this is because from here to here, because G1 and G2 are groups. Multiplication is associated in each of those groups. And this is exactly the product of x1, x2 with y1, z1, comma, y2, z2. And this is exactly x1, x2 times, and this is the product of y1, y2 and z1, z2. So that's a proof of associativity in G1 plus G2. This times the Z is the first times the Y times the Z. That's the proof of associativity. That's the most complicated. what is the identity? If I take any element, x1, x2, in G1 cross G2, I take E1, E2 times x1, x2. That's E1, x1, E2, x2. But E1 is the identity in G1, so E1, x1 is x1. E2 is the identity in G2, so E2, x2 is x2. So if I take any element and I multiply it on the left, I get back the element. Similarly, if I take any element and multiply it on the right by E1, E2, I get x1, E1, x2, E2, which is again x1, x2. So you put these together and you conclude that E1, E2 is the identity element in the product with G1 plus G2. Part B. Part C, the x1, x2 being G1 cross G2. So because G1 and G2 are groups, again, we can say that there exists x1 inverse in G1 and x2 inverse in G2, such that x1, x1 inverse, and x1 inverse x1 equals the identity in G1. And x2, x2 inverse, and x2 inverse x2 is the identity in G2. So if I take x1, x2 in the product group, and I multiply it by the element x1 inverse, x2 inverse, again, multiplication is coordinate-wise. This is x1, x1 inverse, x2, x2 inverse. That's E1, E2. So this is a right inverse to x1, x2, and if I multiply on the left, I get x1 inverse x1, x2 inverse x2. You get E1, E2. Again, so x1, x2 inverse, the inverse of this element is x1 inverse, x2 inverse. So therefore, G1 cross G2 is a group. And if both, not just one, but if both G1 and G2 are abelian, that means if I take x1, x2 times y1, y2, I take the product of any two elements. That's x1, y1, x2, y2. But G1 is abelian, so x1, y1 is y1, x1. And G2 is abelian, so x2, y2 is y2, x2. And this is exactly the product of y1, y2 with x1, x2. So if G1 and G2 are abelian, then G1 times G2 is abelian. Any questions about this? So these are the three group theory questions on the exam. Straightforward. You really use only the basic definitions of algebra. All right, problems 4, 5, and 6 are ring theory problems. So in problem 4, we let R be the set of all rational numbers, all fractions, where the denominator is a power of 5. So the numerator can be any integer, and the denominator is 5 to the k, where k is also any integer. And we define addition and multiplication the way we usually define addition and multiplication. So this is a subset of the rational numbers, and we're adding and subtracting, multiplying and dividing fractions. So just what you learn in elementary school. So if you have a over 5 to the k plus, let's say, b over 5 to the l. I mean, in elementary school, they teach you put things over a common denominator. It doesn't have to be a least common denominator. For example, you could multiply a over 5 to the k, the numerator and denominator, by 5 to the l. A times 5 to the l over 5 to the k times 5 to the l. You can take this fraction and multiply the numerator and denominator by 5 to the k. So I have 5 to the l, 5 to the k. So now I have a common denominator. I have a times 5 to the l over 5 to the k plus l, plus b times 5 to the k over 5 to the k plus l. So that's equal to 5 to the k plus l, a times 5 to the l, plus b times 5 to the k. So this is some element in R. This is not necessarily reduced to lowest terms, but it clearly is a fraction where the denominator is a power of 5. Another approach, no better, no worse. If you have 5 to the k and 5 to the l, if they're not equal, let's say that k is less than or equal to l. So you take a over 5 to the k plus b over 5 to the l, and multiply this fraction, the numerator and denominator, by 5 to the l minus k. So what we get is a times 5 to the l minus k is some non-negative integer. 5 to the k times 5 to the l minus k is 5 to the l, plus b over 5 to the l. Again, we have common denominator. So this is a times 5 to the l minus k plus b over 5 to the l. Again, this is an R. And of course, there's only one way to add fractions, or when you add them, you only get one answer. I have this and I have this, and they have to be the same. You know, this might be divisible. This might not be in lowest terms. Even this might not be in lowest terms. When they're reduced to lowest terms, though, you always get the same number. So R is closed under addition. And if I made this subtraction, if I were subtracting, everything would be basically the same, except you would have a minus sign in the middle. So R is closed under addition and subtraction. Also, I can write 0 as, let's say, 0 over 5. So this is a fraction where the denominator is 5. So this is also in R. So therefore, R is an additive subgroup of the rational numbers. That's part of what you need to prove to show that it's a ring. What about under multiplication? Well, multiplication is even easier. We want to show R is closed under multiplication. So if you have a over 5 to the k times b over 5 to the l, you're just multiplying fractions. This is ab over 5 to the k plus l. Again, this is an integer divided by a power of 5, so this is an R. And if you worry about the multiplicative identity 1 is 5 over 5. So that's also an R. So All the other properties of a ring, well, they're satisfied for the rationals. We know the rationals are a ring, so the distributive laws and so forth, they certainly hold in R. So therefore, R is a subring of the ring of rational numbers Q. Therefore, R is also a commutative ring because multiplication in Q is commutative, right? If I multiplied in the opposite order, I would get BA over 5 to the L plus K, which is the same as AB over 5 to the K plus L, which is A over 5 to the K, B over 5 plus L, 5 to the L. But I don't even have to write this down because the real numbers and the rational numbers are commutative rings. So that proves A. R is a commutative ring. What is a unit? Recall that X is a unit in a ring R if there exists an element Y in R such that XY and YX equal the identity 1, the multiplicative identity. So suppose I take X equal to 25, which I can think of as 25 over 1, or 25 over 5 to the 0. This is certainly in R. I take Y equal to 1 over 25. That's 1 over 5 squared. This is, again, a fraction where the denominator is a power of 5. So this is an R. And 25 times 1 over 25 is 1. So 25 is a unit in R. Its inverse, 1 over 25, is also in R. Any questions? Okay. Part C is to prove that R star, which is the group of units in R, is exactly the set of all powers of 5, 5 to the K, K and Z. I mean, what is 5 to the K, K and Z? What is that set? So you have the positive powers. First of all, you have K to the 0. K equals 0. 5 to the 0 is 1. 5 to the first power, 5 to the second power, 25, 5 cubed. You have the positive powers of 5, but you also have the negative powers of 5, which is 1/5. 5 to the minus 2 is 125. 5 to the minus 3 is 1 over 125, and so forth. These are the powers of 5, positive and negative. And I want to show that this is the group of units. So first of all, you have 5 to the K times 5 to the minus K equals 1 for all K and Z. So 5 to the K is a unit for all K and Z. So every element in this set is certainly a unit because its inverse, the inverse of a power of 5 is another power of 5, which we're allowing positive and negative exponents. But we want to show that every unit has to be a power of 5. So let a over 5 to the k in R be a unit. And we can assume, so reduce the fraction to lowest terms. What that means is a, the numerator, is not divisible by 5. Right? If a were divisible by 5, you would cancel. And k greater than or equal to 0. If k were negative, a over 5 to the k would just be an integer. Actually, the answer this is everything here is a unit, but these aren't the only units because I should have made this more clear. Plus or minus 5 to the k. If you take x equal to minus 1/5, the inverse is minus 5, because minus 1/5 times minus 5 is plus 1. And in general, if I take minus 1 over 5 to the k, and I multiply it by minus 5 to the k, again, I get 1. So the group of units is really going to be the positive and negative powers of 5. Didn't bother me. So suppose we let a over 5 to the k be a unit.
Professor, you mind showing again the last page, please?
Sorry?
Can you show again the last page that you just finished?
Sure. So if I take a number like minus 5 and I multiply it by minus 1/5. So you can think of, if you like, minus 5 is the fraction minus 5 over 1, or 5 to the 0, times minus 1 over 5 to the first power. Right? I mean, this is minus 5. This is minus 1/5. But minus 5 times minus 1/5 is 1. So minus 5 is a unit. And minus 1/5 is a unit. And in general, if I take minus 5 to the k, and I multiply it by minus 1 over 5 to the k, the minuses cancel. I get 5 to the k over 5 to the k, which is 1. So minus 5 to the k is a unit for all integers k. So the group of units in R is plus or minus the positive and negative powers of 5. I shouldn't forget the negative. I shouldn't forget minus 5 to the k also.
Thank you.
So suppose I a over 5 to the k a unit, and a and 5 are relatively prime. 5 does not divide a. But I know what the inverse of a over 5 to the k is. It's 5 to the k over a. And this is in R if and only if a, the denominator, is the power of 5. But 5 does not divide a. So a can only be 5 to the 0 or 1. Or minus 1. maybe to make this clearer, let's say there are two cases. In the first case, A is positive. So in that case, but A over 5 to the K, the inverse is 5 to the K over A. So A is a positive number. It's a power of 5, but it's not divisible by 5. So A has to equal 1. And A over 5 to the K is 1 over 5 to the K, which is 5 to the minus K, which is, that's what I said, a unit is plus or minus a power of 5. If A is negative, let's say A equals minus B, then A over 5 to the K is minus B over 5 to the K. The inverse is minus 5 to the K over B, and B has to equal 1, so because B is a power of 5 and not divisible by 5. So this is minus 5 to the K. So the only possible roots, the only possible units are the positive and negative powers of 5. And the power can be positive or negative as well. For example, if you let x be equal to, let's say, 2/3, sorry, if you let x be equal to 2/5, which is an element of R, x inverse is 5/2. But that's not an element of R because the denominator, 2, is not a power of 5. And so 2/5, that's a fraction where the denominator is 5, but its inverse does not have denominator 5. So it's not an R. So the inverse of 2/5 is not a unit. All right, any questions? That's problem 4. Let's look at problem 5. Suppose we take Z mod 9Z. These are the congruence classes mod 9. Which is a commutative ring. It's our basic finite commutative ring where x plus 9z plus y plus 9z is x plus y plus 9z. That's how you add congruence classes. And x plus 9z times y plus 9z is xy plus 9z. That's how you multiply congruence classes. What are the units? Well, z plus 9, z mod 9z, this has 9 elements. 9z, 1 plus 9z, 2 plus 9z, and so forth, up to 8 plus 9z. What are the units? Well, 1 plus 9z, so the identity, of course, what is the multiplicative identity? It's 1 plus 9z. So if I take certainly 1 plus 9z times 1 plus 9z, I get 1 plus 9z. So 1 plus 9z is certainly a unit. What about 2 plus 9z? If I take 2 plus 9z and multiply by 5 plus 9z, I get 10 plus 9z. And 10 is congruent to 1, so this is the same as 1 plus 9z. So this is a unit, this is a unit, and this is a unit. If I take 4 plus 9z and multiply it by, should I multiply it by? 7 plus 9z, I get 28 plus 9z. That's 4 times 7 is 28. And 28 is the same as 1 mod 9. So this is 1 plus 9z. So 4 plus 9z and 7 plus 9z, these are also units. And if I take 8 plus 9z times 8 plus 9z, I get 64 plus 9z. But again, 64 is congruent to 1 mod 9. So this is equal to 1 plus 9z. So I have 8 plus 9z. So I just found 6 units corresponding to the congruence classes for 1, 2, 4, 5, 7, and 8. So this calculation shows that Z mod 9Z, the group of units, certainly contains the congruence classes 1 plus 9Z, 2 plus 9Z, 4 plus 9Z, 5 plus 9Z, 7 plus 9Z, and 8 plus 9Z, those 6 congruence classes. What are missing? Well, 0, 3, and 6. So 0 plus 9Z times any x plus 9Z is 0 plus 9Z. It's definitely not 1 plus 9Z. So 0 plus 9Z or 9Z is not a unit. That's clear. If you had 3 plus 9Z times x plus 9z, which is 3x plus 9z, if you could find an x such that this was 1 plus 9z, that would be true if and only if you could solve the congruence 3x congruent to 1 mod 9. But this is impossible. There's no solution to this congruence. Because this would say 3x is equal to 1 plus 9y for some x and y, and that would mean 3 divides 1, which is false. So 3 plus 9z is not a unit. And similarly, if you had 6 plus 9z, if 6 plus 9z were a unit, there would be a congruence class x plus 9z, where this product 6x plus 9z was 1 plus 9z, which would mean that 6x is congruent to 1 mod 9, or 6s is 1 plus 9y for some y. But these are divisible by 3, which means 3 divides 1 again, which is impossible. So the non-units in Z mod 9Z are Z, 3 plus 9Z, and 6 plus 9Z. So in fact, this set of 6 elements is the group of units in Z mod 9Z. The units are the congruence classes of 1, 2, 4, 5, 7, and 8. On the other hand, 3 plus 9z is not 0, but 3 plus 9z times 3 plus 9z is 3 times 3 plus 9z, which is 9 plus 9z, which is 9z. So I have a product of 2 elements that gives 0. So Z mod 9Z is not an integral domain. So all of that is part A of the problem. Okay, what about part B? In part B, we have Z mod 5Z. Congruence class is mod 5. So this is a ring with 5 elements. And the identity element is 1 plus 5Z. And if you check, 2 plus 5Z times 3 plus 5Z is 6 plus 5Z. 6 is congruent to 1 mod 5Z. So the group of units, Z mod 5Z star, it certainly contains the identity, 1. It contains 2 and 3, 2 plus 5Z, 3 plus 5Z. And if I take 4 plus 5Z and multiply it by itself, 4 times 4 is 16. And 16 is congruent to 1 mod 5, so this is 1 plus 5Z. So 4 plus 5Z is also a unit. 0 is never a unit. So every non-zero congruence class, every non-zero element of Z mod 5Z is a unit. So that tells us what the units are, and therefore Z mod 5Z is a field. Because a field is, by definition, a ring, a commutative ring in which every non-zero element is a unit, has an index. So that's part B. Okay. Last problem, problem 6. We have a set of real numbers, which we denote by Z square brackets square root of 5. This is all numbers of the form A plus B times the square root of 5, where A and B are integers. So A and B are integers, square root of 5 is a real number. This is some subset of the reals. These aren't rational numbers, they're not fractions, but they're all real numbers. And we define a function called n that associates to every element of the set an integer. And we define it by n, we call this the norm. The norm of this number a plus b root 5 is a squared minus 5b squared. So a and b are integers, so this is definitely an integer. Positive, negative, or 0. So that's a simple definition. So if you do the calculation, for example, of 2 minus 3 root 5, so if you compare it to this, a is 2, b is minus 3. So this is 2 squared minus 5 times minus 3 squared. That's 4 minus 5 times 9 is 45. That's minus 41. That's this one. Oh, no, that's part of the problem. So let me just skip it. So if I let x be 2 minus 3 root 5 and y be 4 minus root 5. So what I just calculated is the norm of x. If x and y are these two numbers, if I add them, x plus y is 2 minus 3 root 5 plus 4 minus root 5. That's equal to 6 minus 4 root 5. And if I multiply them, 2 minus 3 root 5 times 4 minus root 5, that's 2 times this, 8 minus 2 root 5, minus 3 times this, which is minus 12 root 5, plus 3 times root 5 times root 5. Root 5 times root 5 is 5. 3 times 5 is 15. 15 plus 8 is 23. 23 minus 24 root 5. Let me just double check. 8 plus 15 is 23. Minus 2 minus 12. Oops, should be minus 14. Oh, yeah, this is a 2. Minus 2 minus 12 is minus 14. Good to do arithmetic correctly. It's always good to check. Minus 2 minus 12 minus 14. Okay. So that's x plus y, x times y, and the norm of x. We want to show this set is a ring. So it's contained in R, so really showing that it's a subring of the real numbers. It has to be closed under addition. So if you have a plus b root 5 plus c plus d root 5, that's easy enough. That's a plus c plus b plus d root 5. So this is still in z squared brackets root 5. So this is closed under addition. And if I were subtracting, we'll just get these integers. A, B, C, and D are integers. So A plus or minus C and B plus or minus D are integers. So this is, and I have to show that it's closed under multiplication. And also, of course, 0 is 0 plus 0 root 5. So that's certainly in here. Just as 1 is 1 plus 0 root 5 is in this ring. And if I take A plus B root 5 times C plus D root 5, if I multiply through, I get AC plus AD root 5 plus BC root 5 plus BD root 5 times root 5. This is AC root 5 squared is 5 plus 5BD plus AD plus BC root 5. This is an integer and this is an integer. So this is also in this set of real numbers. So this is a subring of the reals and it's a ring. That's nice. See, there's another typo. The other typo just made it slightly easier, but that's okay. Part C, if x is a plus b root 5, and y is c plus, I just wrote root 5 in the notes. It should have been d root 5, but it's easy enough. This is just the case d equal 1. So if you did what you were supposed to do, it's Perfectly fine. And x times y, I just calculated that. AC plus 5BD plus AD plus BC root 5. So the norm of xy is AC plus 5BD squared minus 5 times AD plus 5BC squared. So this is just a little bit of high school algebra. This is A squared C squared plus 10 ABCD plus 25 B squared D squared minus 5 times A squared D squared plus 2 ABCD plus B squared C squared. Let's see, here I have plus 10 ABCD. Here, minus 5 times 2, I have minus 10 ABCD. So these terms cancel out. So what I get is A squared C squared minus 5 A squared D squared plus, let me just write this, minus 5 A squared D squared plus 25 B squared D squared. Here I can factor out an A squared. I get A squared times C squared minus 5B squared. Here, if I factor out a 5B squared, I get A squared minus 5B squared. Let's see if I did it wrong. A squared times C squared minus 5B squared. So this is 25B squared B squared. Let me just do this a little bit more carefully. It's a question of how to do it. AC plus 5BD squared minus 5AB plus BC squared. A squared C squared 10 ABCD 25 B squared B squared minus 5 A squared B squared. So this is correct. And these terms cancel. And I have A squared times C squared minus 5B squared. And here, let's see. Look at the two remaining terms. So I get A squared C squared minus 5A squared B squared. And I have minus 5 B squared C squared plus 25 B squared B squared. So if I factor a minus 5 B squared from that, I get C squared minus 5B squared. So this is, and I can factor out C squared minus 5B squared. I get A squared minus 5B squared, C squared minus 5B squared. And that is the norm of x times the norm of y. That's what I wanted to show. So that's the proof. That's the whole exam. Any questions about that? All right, so maybe I'll stop here for today. And I think we have 2 more classes in the semester. I think we're going to spend both classes reviewing material for the final. So I will send out some review sheets that cover the entire class, the entire course, and those I will be covering on Wednesday of this week and Monday of next week. And I remind you that the final exam is on Monday, May 23rd. And according to the Lehman College final exam schedule, for 9 o'clock class, the final exam actually starts at 8:30. So the exam will be 8:30. If there are no questions, then you're done for the morning. You're well up.